So for problem number 3A, it says find the velocity of the bullet block system after the collision. Now I know a lot of students want to use conservation of momentum to solve this, but in the scenario they give you the distance of x from the edge of the table and the height of h. So because they give us those variables, generally it means that they want us to use those variables in our equation when we derive it. So you're going to need to use conservation of momentum anyway, but I would solve this first using kinematics. So anytime you're trying to find the final velocity, in this scenario, we want the final velocity when the bullet gets embedded into the block, and then as one unit they start traveling in a certain velocity v. So that velocity, because it's on a frictionless table, is going to stay constant in the x direction, and then when it launches off of the table it's going to have a y component due to gravity pulling it down. So anytime you solve kinematic equations, you generally want to start with the y component first to solve for time, and then you can plug that time into the x component. So that's what I'm going to start with here. I have a y initial of h, a y final of 0, a v initial of 0, and a v final is unknown. We don't even need that v final. What we need is the time. So I'm going to use the second kinematic equation. This ends up canceling out, and so does that. So I get 0 is equal to h minus 1/2 gt squared, minus because the gravity is going in the negative direction, so I just pulled it out in front. From there, I'm going to subtract the h over and then multiply by 2 and divide by negative g. So that's going to get rid of the negatives, and I get t squared, or sorry, t is equal to the square root of 2h over g. Okay, now we're working with the x component. I'm going to use the same kinematic equation, x equals x naught plus v naught t plus 1/2 at squared. In the x component, the acceleration is 0, and my initial position, I'm going to set that equal to 0. So x is equal to v naught times the time from the y component of 2h over g, and then when I multiply by the reciprocal, I get v naught is equal to x times the square root of g over 2h, and that is the velocity in which the object is launched. So I'm going to change the notation here, because this v naught is not this v naught, it is this. So I'm going to say that the velocity of the bullet block system when they are stuck together is going to fly out at a v of x times the square root of g over 2h. So for part B, I'm finding the initial velocity of the bullet before the collision. I'm solving for, let me use a different color, for this v naught, and I should change this guy here so that I don't use the same notation. This is the final velocity once I collide. So that's the equation for that. To get the initial velocity, I am going to use conservation of momentum. So my p initial is equal to my p final, and since the block is not moving initially, my only momentum is going to be the momentum of the bullet, and then my final momentum is going to be the combination of the bullet block and its final velocity, which I get from here. So I'm going to solve for this v naught, and let me plug in my velocity from part A first. So I get x times the square root of g over 2h, and I'm going to isolate this V naught here, and then from there I am going to simply divide the M over. So I get V naught is equal to M plus big M over little m times x to the square root of g over 2h. So it's not pretty, but this is my V initial. All right, so for part C, we want the ratio between the initial kinetic energy over the final kinetic energy, and the initial kinetic energy is just the bullet launching toward the block. So I have 1/2 m V naught squared, and I already solved for V naught, which is in part B, so that's going to be this long equation. And this whole quantity is squared all over the final kinetic energy, which is the bullet and block stuck together, times the velocity I get from part A, which is x times the square root of g over 2. Oops, that should be a g over 2h quantity squared. Okay, a lot of things are going to end up canceling, but one thing I need to make sure to do is that if I have a squared out here, it's going to distribute, so I'm going to take that away, square this, and square this. And then I can start reducing this m with that m, the 1/2 with that 1/2, this m plus m with one of those m plus m's, and then this whole x square root of g over 2h squared ends up canceling there. And in the end, I end up with m plus m, big M, over little m as my ratio.